Yes.
Hey, so welcome everyone. Today we're very excited to have Wang from NYU who will speak about Kakeya sets in R3.
Okay. Thank you very much for the invitation. It's a great pleasure to, a great honor to come to University of Chicago to talk about Kakeya sets. This is joint work with George Zhao. So a Kakeya set in Rn is a compact subset that contains a unit line segment in every direction. Can people see what I write? Okay. So when we look at the definition of a Kakeya set, an immediate example that comes to mind is this unit disk. So with everything in between, then unit ball. Then the question is, can you make the Kakeya set slightly smaller? For instance, this is the equilateral triangle, and then if we are interested in the directions in this 60-degree angle, then we can cut this triangle into half and then move the halves closer. Then this still we still have all the unit line segments in this 60 angle direction, so they are still here. So, but when we move it closer, the area so here this is an example in R2, the area becomes smaller. And we can iterate this process. Say, now we cut it into 4 parts. This is an example that has smaller and smaller area, but still keeping all the unit line segments in this 60-degree angle. So if you iterate this process, in the end, you will get a set of measured zero of arbitrary small measures such that it contains all the unit line segment in this 60-degree angle, and then we can rotate and have like six copies to make it into a Kakeya set with zero measure. So this was Professor so he constructed in 1919 that Kakeya set of zero Lebesgue measure. So now that we know it can be arbitrarily small, then the next question is how small can it be? So this is a Kakeya conjecture. Kakeya set conjecture says that any Kakeya set in Rn has Hausdorff dimension n. So in this lecture, let's pretend that Hausdorff dimension means the following. This is not rigorous and not true, but it's helpful to have this intuition. So E in Rn has dimension n. So this is a big quotation mark. Is equivalent to say that for any small delta that goes to 0. If we take our delta neighborhood of E, the measure is, let's say, let's say dimension S, approximately n minus S. Again, this is not rigorous at all, but let's use this to serve as an intuition. And why do we care about this conjecture? So Charles Fetterman used as a college set, the Kakeya set of zero Lebesgue measure to construct a counterexample, the ball to the ball multiplier conjecture. So this is about the convergence of Fourier transform. For instance, we have a function, and then we take its Fourier transform, and then we take the inverse Fourier transform. We know that it should recover the function. But then the question is, if you take the Fourier transform and restrict it to a large ball and let the radius of the ball goes to infinity, does it still converge to F? Well, surprisingly, the answer is no in some sense, and then the reason why the answer is no in that sense is precisely because the Kakeya set could have zero Lebesgue measure. Also, this Kakeya conjecture is connected to problems in harmonic analysis, and it's also connected to problems in number theory. And also in homogeneous dynamics, and dynamics in general. I recently learned of this connection. So let me talk about history. So the dimension n was solved by Davis in 1971, and the dimension 3, that's what we are focusing today. There has been several results in the past. So Bourgain proved in 1991 that the Hausdorff dimension of the Kakeya set should be greater or equal than 2 plus 1/3. And Tom Wolf proved in 1995 that the Hausdorff dimension should be greater or equal than 2 plus 1/2. And then there is a result of Katz, Lapa, and Tao. They show that there exists some positive epsilon such that the Minkowski dimension of a Kakeya set is greater or equal than 2 plus 1/2 plus epsilon. And this year, joined with Josh Zhao, we proved that it should have Hausdorff dimension 3. And it's still open in dimension greater or equal than 4. Yes?
I was just wondering, could you clarify with this Hausdorff dimension, like when S is n and you were saying that this is like
1.
Yeah.
Approximately 1. Why this is true?
Yeah, I guess I just don't. I'm very sure.
For example, this unit disk, you take delta neighborhood, it's still like 1 plus delta disk. And the volume of a 1 plus delta disk is like between 1 and 2, for example, or between 1 and 10. So this is what I mean. If you take S to be n, then this is 0 and it's 1. Approximately means up to constant multiplying.
But I guess with like the spiky thing, if you like measure 0 and you like take a delta neighborhood of it?
Yeah, that's a great question. So this is what I will specify in the end. So what this means is, in reality, should be up to arbitrary small powers of delta. So, and this spiky example, I think it's true if it's like 1 over log delta, something like that. But this 1 over log delta is absorbed in this approximate.
Okay.
Thanks for the question. Yeah. Also, this is by no means rigorous. So, and probably you have noticed that there is this 2 plus 1/2, and this the result of Katz, Laba, and Tau, even though it's an absolute improvement, but it's a big breakthrough because it overcomes a series of obstacles in the study of the Kakeya sets in R3. So. This is because there is the Heisenberg group example. So the Heisenberg group is the. I'm writing the definition here in case you're interested, but I won't have time to go into details. This example is sharp for Wolf's argument. It is a set that contains It's a set that has all the properties that Tom Wolf used to prove that the Kakeya set should have dimension greater or equal than 2 plus 1/2. And the work of Katz, Laba, and Tau, what they did is they showed that if a Kakeya set were to have Minkowski dimension 2 plus 1/2, then it should resemble the Heisenberg group. In particular, it should have the 3 properties: stickiness, planiness, and graininess. So the notion of stickiness is going to play an important role. So what does sticky Kakeya set means? It means that a Kakeya set contains many line segments. So if we have 2 line segments that has, say, angle, say, rho, then sticky means that you can find approximately a tube of radius approximately rho that a length 1 that covers it. So this is sticky, but non-sticky means the following. Sticky means any pair of line segments that has angle some number that you should have a tube of comparable radius that contains it. So non-sticky means that these 2 line segments might have a very close angle, but they are far apart, so you cannot find a common ball of radius rho a common tube of radius rho to cover it. So this is sticky and this is non-sticky. Then, for the graininess property, I'm going to draw a picture to summarize what we know before. So the picture is the following. Graininess means that the Kakeya set is organized into this small slabs, planar slabs, and so that So that any line that intersect this line, then it should intersect it tangential to this little slab, and this is what we call grain. And the Kakeya set can be decomposed into a union of slabs. The difficulty that so people know this picture before, and this also this picture appeared in the work of Kaslab and Chow. This picture is also appeared in this example if you spend some time to calculate this example. And this picture also appeared in the work of Booth, where he showed that if you have a hypothetical counterexample to the Kakeya conjecture, then it should look like this. But then the difficulty is that those grains are little planar slab. Are not they are not in the same direction, even along the same line. They kind of rotate, and this is the difficulty. So just a very quick comment on what we did to those grains is the following. So we realized that we should just consider how those grains intersect, like the grains from different lines intersect. The grain that sits on different lines intersect. So previously, I thought that, at least several years ago, I thought that since the difficulty is that the grains sort of rotate, maybe one should try to understand how the directions of the grain on the same line. But this turns out to be not that relevant for the problem. So what's more relevant is, in fact, you take a small ball to cover those grains, and then just study how the grains inside a small ball intersect. So we'll go back to this picture in the end, but this is I try to explain how I visualize Kakeya set in R3 and where the difficulty is. So yeah, I'm not very precise here, but let's say the Kakeya set in R3. So it should be locally it should be a union of those two-dimensional little slabs. That's what I mean by grains. And also the two-dimensional little slabs interact with the line in the sense that if a line intersects a grain, it should go through it tangentially. Yeah, done.
And are the slabs thickened, or are they just two-dimensional?
We should think as they are two-dimensional. Very quickly, I will go to a delta thickening of the problem, and the slab has thickness delta, so it's like just two-dimensional. Are there more questions? Okay. So that is how what we know about Kakeya set. Like this picture sort of summarized it maybe 10 years ago, or 5 or 10 years ago. Then our approach to the Kakeya set in R3 is closely related to some progress in projection theory in the past maybe 5-6 years. So what projection theory is doing. So we'll put the study of the Kakeya set in a more general context. That's the projection theory. It studies, say, we have a subspace in Rn. Let's say V is a n-dimensional subspace. And we study the orthogonal projection from Rn to V. So orthogonal projection. And the projection theory studies if we have a Borel subset of Rn, and we have a collection of n-dimensional subspaces then what can we say about the Hausdorff dimension of the projection image? So the picture is like if we have some set here and then we have some subspace V and we project, and we want to understand the projection image of the set. So in fact, the general Kakeya conjecture can be reformulated as a problem about projection, but I won't do it here. And then for the past few years, so the study of projection theory has the following common thing. That is, we first, let me erase this picture. We first study the problem and for a special class of sets that's called sticky sets, or some also related to it's almost alpha's regular set. So those sticky almost alpha's regular set, they are generalization of some natural generalization of self-similar set. For example, that example is almost alpha's regular set, or is also a sticky set, the Basic-College example. And those sets have similar properties at all scales. So it has a very rigid structure, and so it's relatively easier to study the problem within this class. So this is a special class, and people find out that it's easier to study problems in this special class because it obeys very similar property and it's easier to do inductions. And then there is the problem of how to go from sticky sets to general sets. So for this, we use inductional scales. Okay. So the idea is that we use the results about sticky sets as a black box, and then try to design induction scales according to the problem we want to study. So this is all very abstract. I want to emphasize. I want to say that there are several problems that there are not several, just a couple of problems that we succeeded. For instance, the Furstenberg set conjecture was proved this way, and also the Kakeya set in R3, we proved it in this way. There are still some open problems where people know how to prove for sticky case, but we still don't know how to do the general case. So just to say why this general scheme is useful. So for the Heisenberg group example, it's to improve this 5 halves bound, we need to distinguish the Heisenberg group and the Kakeya set. So it's very hard because we don't know what properties we should use we can use to distinguish the Heisenberg group and the Kakeya set. So at the beginning, we might think that, okay, the Heisenberg group does not really contain a complex line in every direction. It has some small family of parallel lines. Maybe that is the property we should use, but it's very hard to use it, mostly because we don't know how to do induction with this property. So it turns out that at least the way we distinguish Heisenberg group and the Kakeya set is to explore that the Heisenberg group lies in C3. but the Kakeya set has to lie in Rn. And to distinguish this, we use Bourgain's sum product. So within the sticky set class is because it's more rigid, so it's easier to draw some sort of contradiction and apply the Bourgain's discretized sum product. Okay. So this is what we do. So inspired by some arguments of Katz and Tao, like Tao's blog post, we prove that. So our first step is to prove the Kakeya set conjecture in R3 holds for this special class. So any sticky Kakeya set in R3 has Hausdorff dimension 3. And this is the place that we rule out the Heisenberg group example. And also this is the place that we applied some Bourgain's sum product estimate. So at this stage, the Heisenberg group example is gone. And today we are focusing on how to apply this result as a black box to obtain the same result for general sets, for general Kakeya sets. So are there any questions? I hope I can be more precise later, but for now.
State set result is the one we proved a couple years ago.
Yes. So we proved this on arXiv on 2022.
Just to clarify, so the Heisenberg group is sticky but not Kakeya? Or
Yes, it's sticky but not Kakeya. And the way we show that it's not Kakeya is by applying Bourgain's sum product estimates to say that Heisenberg group has to lie in C3. It cannot be nothing can be like Heisenberg group in R3. Okay. So now the sticky sets are sort of very rigid, and for general Kakeya set, it's a huge class. And so how to do inductions and how to reduce the problem about general Kakeya sets to sticky sets. So the starting point is to find the right induction hypothesis. So sometimes when we want to apply induction, we need to find the right class of objects that is general enough so that we can run the induction, but not too general so that the conclusion is false. So that's our starting point. So let's first just translate the Kakeya problem to a discretized problem. Let's say delta is a small scale that's very small, that's much less than 1 and positive. And say T is a set of delta tubes contained in, let's say, a ball of radius 2. So here delta tubes means length 1 and radius delta. So this. And the Kakeya's assumption says that T should contain a delta tube in every delta separated this is the Kakeya assumption. It contains a unit line segment in every direction, and we just thicken this unit line by delta. Then the conjecture is the following. So if T satisfies the Kakeya assumption, then the union of those tubes has volume approximately 1. So this approximately 1 is up to like negligible powers of delta. And also this Kakeya assumption, as you can see, that implies that the number of tubes should be greater than delta to the minus 2. So for now, we focus on R3. So if one can prove this discretized conjecture, then we prove the Kakeya conjecture in R3. But this Kakeya assumption turns out to be very hard to do any induction on it. So the reason is that if we have a set of delta tubes that contains a delta tube in every delta separated direction, and to do some induction on scales, what we do is we cover the Kakeya set by some smaller boxes, and then we want to run the induction. We say that we know what happens in the smaller box, and we want to know what happens in general. So, but then the issue is that if we cover it by some smaller box, there is no reason why those segments still have separate direction, and also no reason that in every separate direction we have a tube. And so it's the same issue for those thick tubes. If we make the box longer, then there is no reason why it should contain a delta tube in every delta separated direction within this red box. This is in particular false for non-sticky set. So here the tubes are sort of sparse, and then within each thick tube, there are not too many thin tubes. So the issue is that Kakeya assumption is bad for induction. So are there any questions so far? And so what happens if we just use this assumption instead? Say that the number of tubes is greater than delta to the minus 2. Then this is false for the following reason. So if the number of tubes to be approximately delta to the minus 2, we can take a slab of size 1 times 1 times delta, and then we take T to be all the distinct tubes contained in the slab. So T are distinct delta tubes contained in this, let's call the slab S. Then distinct means T1 intersect T2 should be less than half of the volume of T. Then we can count that in each direction we can insert delta to the minus 1 many parallel delta tubes in S, and we have delta to the minus 1 many distinct directions. So the number of tubes is approximately delta to the minus 2. But then the union has volume delta because it has most the volume of the slab. So we cannot just say that let's try to prove the result assuming just the number of tubes is delta to the minus 2. And this Kakeya assumption is very hard to use. What can we do? It turns out that in R3, and this is some variance of this is the only obstacles. So we need to come up with some assumption about the set of tubes that says that says the tubes cannot be concentrated on smaller convex sets. So this is the definition of the induction hypothesis we are going to use. So let's say T is a set of delta tubes contained in a ball of radius 2. Then we say that T satisfies the Kakeya-Wolf axiom. So we write it to be KT. Kakeya. If for any convex set, we should really think those as rectangular box. We use the notation T bracket U as the set of T that's contained in U. We have the number of tubes contained in U is less than some constant times the volume of U divided by the volume of T. So this means that there are not too many tubes contained in any convex set. And there is sort of dual definition. We say that T satisfies Frostman Wolf axiom. If, again, for any convex set U, the number of tubes contained in U is less than the volume of U times the total number of tubes. So both definitions rule out this enemy example that the tubes are entirely contained in some slab. So many tubes are contained in a slab. So the first definition is closely related to what Wolf used to prove his 5 halves bound. What he showed is that suppose T is a set of tubes that satisfy the first axiom, then it should have the dimension at least 5 halves. And again, the Heisenberg group is sharp for this argument because Wolf's argument didn't specify whether we are in R3 or C3. But since we have this sticky result that rules out rules out the Heisenberg group, so assuming this as a black box, we could hope to say that we can work with this class of tubes and prove the result. And so what is the result that we proved? Is the following. We show that if the tube satisfies the Kakeya-Wolf axiom, then they should be essentially disjoint. Means that the union of those tubes has volume approximately the number of tubes times the volume of a single tube. And then, so if the set of tubes is satisfy the Frostman-Wolf axiom, then they should steer out the ball. So it means that it has volume approximately 1. Again, this approximately 1 absorbs like epsilon powers of delta. So this is what we proved. And one can show that Kakeya assumption implies both Cat-Tau and Frostman axiom. So in particular, if a set of tubes satisfy the Kakeya assumption, then the conjecture is true that the union of those tubes in T should have volume approximately 1 up to subpolynomial powers of delta. Okay, are there any questions about it? Yes?
Maybe this is better for after, but is it, can you quickly say how you go, because the Kakeya assumption, can you quickly say how you go from the Kakeya assumption to, like that first seems to get like a lower bound on the number of size of T, and here you're getting like upper bound on the size of T.
So this is, in fact, a lower bound on the size of T.
Oh, but the first one is...
Yeah, the first one says that, okay, so when I say the Kakeya assumption implies both Cat-Tau, I mean that if T has exactly 1 tube in each delta separated direction, then the number of tubes should be delta to the minus 2. When the number of tubes is approximately delta to the minus 2, these two assumptions are equivalent. Are there more questions? So, okay. Now it's a good time to... So the proof idea is just to study any arbitrary collection, general collection of tubes, and then try to decompose it into these two classes. But to start with, let's say that we have a set of tubes. Let's say, assume that the number of tubes is about delta to the minus 2, and so it's both Cat-Tau and Frostman. Also, assume that it's not sticky. Otherwise, we are done. Then not sticky here means the following. It means that the number of row tubes, so means that there exists some row between delta and 1. The number of row tubes required to cover T is much greater than row to the minus 2. So just the starting point is that we have a set of tubes that's required a lot of row tubes to cover it. So it's like in this picture, it requires a lot of row tubes to cover it. Then we study the multiplicity of a typical point. So we define mu T as the number of tubes through a typical point. So here it is the number of tubes times the volume of a tube divided by the volume of a set. And we have some strategy. So the winning strategy so either we show that the multiplicity is small, or we show that there exists some tau greater than delta, such that the union of tubes intersect some ball, a typical ball of radius tau is large. So those are two strategies. In reality, we have more strategies, but let's say we focus on these two. So now we want to do induction on scales. So let's look at the picture. Let's say this multiplicity is the number of tubes through a typical point. At this point, the multiplicity in the picture is 4 because there are 4 tubes through it. And then we look at so we want to do induction scales. We first look at the set of tubes contained in a row tube. And so this we can apply induction. So the reason why we can apply induction is because this Cat-Wolf axiom is preserved if we restrict to thin tubes in a thick tube. So if we just restrict to a subset of the tubes, it's still, if it obeys Cat-Wolf axiom, then it's still obeys Cat-Wolf axiom. So for this term, we can apply induction. And then if we want to look at the set of thin tubes in T row, we can see that because they have their angle separation is small, so they intersect into those long segments, those segments of length delta over row. So this is simple, just 2 tubes if their angle is rho, and then the arrow for the thickness is delta, then this length is just delta over rho. So this angle is rho, and then delta divided by rho. So then we can see that the multiplicity of T is decomposed into the number of thin tubes intersect through a point in a thick tube times the number of those segments. We call them grains. The number of segments through a typical point. So we let this G to denote the set of grains. So the grain has dimensions delta times delta times delta over rho. And this is thus bounded by the number of thin tubes through a point in a thick tube times the number of tube segments, the number of grains through each point. So that's the starting point of the induction on scales. I should note that usually in the past we use replace this by is less or equal than mu t rho, like the number of rho tubes through a point. But so this is what people use in the past. But then this way is not efficient because there might be some other rho tubes passing through a point that does not contribute to this multiplicity. This is wasteful, but this is especially wasteful in the non-sticky case because we have a lot of rho tubes. But there is a reason why people use this instead of grains. The reason is that even though this T row does not necessarily obey the Kakeya assumption, but it still has some nice properties coming from the Kakeya assumption. But if we just study this multiplicity of grains, those red segments through each point, there is no a priori assumption on the set of grains. So this set of grains can be arbitrary. It's just a set of tube segments, and we don't know anything about it. And this makes the problem difficult because, as we have seen here, if we don't add any assumption on the set of tubes, then there is no good volume bound. So this is the difficulty, and as you can probably guess, then what we do is we prove a theorem about general sets, about any about union of tubes for any set of tubes. The way to do it is that, so first of all, an easy reduction is to just cover those grains by delta over rho balls because that's their length, and then rescale it. So after rescaling, this becomes rho tubes. So now in this picture, we have an arbitrary set of rho tubes. How do we study it? We prove some factoring lemma or factoring proposition that says that for any set of rho tubes, we can find two numbers A and B, and those complex a set of convex sets. So W of dimension A times B times 1, such that the set of those big boxes obey a natural generalization of the Cat-Wolf Wolf axiom. And then for each, so let's say those tubes, let's say this is T rho. For each W, those rho tubes contained in W satisfies is rescaled Frostman. So rescaled. Now here is the place where we can use our intuition. So this is the theorem we proved, but this also serves as an intuition. Means that if we have a set that's Cat-Tau, they should be essentially disjoint, and if we have a set that's Frostman, it should be essentially fill out the ball. So here in this picture means that those red tubes should fill out those A times B times 1 boxes. So
Let me just say one more time. When you got to the point of the delta over rho ball
tubes.
Tubes, right? The tubes inside of that, you're not using the fact that it satisfies the Kakeya.
No, it doesn't satisfy.
Arbitrary
Yeah, it's
tubes inside. So the rest of this, when you get to KT, and after you're doing it without the Kakeya.
the starting point is already without the Kakeya assumption. So the starting point
The
is
starting point is KT.
Yeah.
But so is there some? But there's nothing. You're getting KT and F
from nothing.
from nothing.
Yes, that's the point of that's the main idea. We get structure from no structure, so we can and then we analyze and then we study case by case according to what we get from this set. So if it's Cat-Tau, then we try to show that the multiplicity is small, and if it's Frostman, then we try to. If it's Frostman, then we can find a tau, a ball such that the intersection is large, because this intuition tells us that it should fill out those W so that a typical ball is very dense, and that's our second strategy. That's a very high level, also not very rigorous explanation of the idea, but I'll stop here. Thank you.
Questions?
Yes.
So where do you use that you're in 3 dimensions instead of higher dimensions?
That's a great question. So we prove. So first of all, the sticky result relies on we are in R3, and then the mode perhaps also. This example contains it's an example in R4. It contains 3-dimensional set of lines. The lines also satisfy the Wolf axioms, and it has dimension 3 instead of 4. But where the proof breaks down, first of all, the conclusion is not true anymore. So we need to replace the convex set by semi-algebraic set, like by neighborhoods of algebraic varieties. And this is one thing to at least to make some statement that's not obviously false. And then where the proof breaks down is in the application of some product in the proof of the sticky the sticky Kakeya set has 4 Haskell dimensions.
Here's a related question: what is the maximum bound for the maximum lower bound of the dimension in a Kakeya set in Rn for n bigger than 3?
I think asymptotically it's like dimension. I just checked it in case someone wants to ask. I think this is something like this, and people prove it using different methods, like arithmetic Kakeya and also polynomial method. Asymptotically, in lower dimension there are some better bounds.
What applications of this step goes into the?
Yeah. So last year with Shukun Wu, we made a conjecture about this. We call it 2n Furstenberg conjectures. It's about union of subset of tubes, and we show that if that's more generalized Kakeya type conjecture is true, then the restriction conjecture is true. Yeah, so that's
So
one.
do you think that this generalized conjecture is true?
In R3, I'm trying to see if it's true.
Well, if there's no more questions, let's thank the speaker again.